Greetings, everyone. Today's lesson is all about the PLC programming basics. I want us to go through the programming languages, the specialized languages that can be used to program our programmable logic controllers. Basically, mostly we have about 5 of the languages. Today, we'll be doing a practical task of how this was done. But I want us just to go through the language. The first language that we have is a ladder logic or ladder diagram. As many of you have been exposed to relay logic, it's just a conversion of a relay logic into a ladder diagram of the PLC that would understand better. And then we have what you call a structured text, ST. This is based on the high-level programming language called C or the Python, the language, the Python language. If many of you have seen, the language of text. You give an instruction, for an example, if you want this simple URL instruction to be executed, you just say if run is true, meaning if the stop button is pressed and the e-stop is not, which would remain in its state, that would be the normally closed state, and not stop and not overload, then command must be set to true, right? So meaning if this is pressed and this is still the way it is, this is the way it is, this is the way it is, then we can set this guy to true, meaning high, and become on. Then we end the if instruction. And then if the stop is true, meaning if the stop is pressed, or if the e-stop is true, or if the overload is true. If either of these conditions is true, meaning pressed, then the command must be set to false. Then we end the if. That's the structured text in layman's term. The function block diagram. Looking at this block, I think this is what we call a derived function block. There is a smaller block that is inside or within this diagram that execute all these to be pushed towards the command. As you can see, the start button will be connected there, the stop button there, and the overload there, and the e-stop there. And then the coil will be connected there. But within the backgrounds, I think as we decode and go through this task on the following lesson, we'll be able to see exactly what's happening here. How was this achieved? Then we have what we call sequential function. This represents the process as a step-by-step sequence. We would have the start of the sequence, let's say for instance, in a DOL kind of a manner. This will be our start of the sequence. Then we'll ask a question: is the sequence ready? If the answer is yes, then we would move to the next question: is the start button pressed? If here the answer was no, then you would have to do a reset in order to restart from zero. And then if the start button is pressed, then we'll move to the next task, which is setting up the command. If the command is set, is the command set? If the answer is yes, then we leave it as is. If the answer is no, then we go back and ask, was the start button pressed? If the start button was pressed, then nothing happened, we would have to go back again. Understand? So it will be like in a sequence like that. That will deal with it as well as we move in this quest of understanding process automation. And we have what we call instruction list in an example attached there. And then without any waste of time, and I want us to actually deal with the practicality of the ladder the ladder logic for today, and then we'll deal with the rest of the languages as we move. We'll do this using, for now, Unity Pro, which is the software version of Schneider Electric, the old version. The new version is called EcoStructure, but it's based on the very same layout as the Unity Pro. Then we're going to create a new project. Then we're going to select any of the PLC rack or PLC CPU that we wanted. Then we're going to double click on the PC bus in order for it to bring us here. As you can see on the layout, on the introduction, we've dealt with this. This is our power supply. And then this is our CPU. This is a rack. Nothing is connected on the rack as it is now in terms of the other modules. We only have the CPU and the power supply. What does our task require us? Our task require us to have a digital output module, because we're going to have the one digital output, which is the coil of the motor. We're going to have 1, 2, 3, 4, and 1, 2, 3, 4, because this would be a latching of that. We're going to have 1, 2, 3, 4 of the digital inputs. So how many modules do we need? We need a digital output module and a digital input module. Then we're going to go to our PLC project and click on the rack and say new device. Under new device, you can see under this CPU, you can or the rack, you can add this type of modules. We're specifically looking for a discrete, other name for digital or digital signal, we call it a discrete signal. We're going to collapse that, and we're going to look for a digital input module, which is DDI, and then we're going to just choose that one. You can choose whatever that you would have been having in hand. We're going to collapse again the discrete, and then we're going to look for DDO, which is a digital output module. The modules are added like that. In each of your project, as you do the programming, you then have to declare your variables, or what we call the things that you will be using on your project. As you can see on this project, we're saying we're going to use a start button, overload, stop, and start, and a motor. We need to declare this so that the PLC can recognize whatever that we have on the system. We're going to go to tools and come to data editor. Then under data editor, there you can see variables. Then click there, and you're going to declare that I have a start button on this PLC, and then I've connected it. Let's say for argument's sake, remember how you declare your or how you address your digital input signals. It's going to be percentage I. We are on rack 0, slot number 1, and then I've connected it on digital input 0, for instance, for example. Then let's just change this to e-board so that we don't experience any problem. Then if you can go to your PLC bar, you see there we have DDI on slot 1. That's why I said slot 1 there. Then I connected it on digital input 0. And if I come here and double click on this module, we'll see there on digital input 0, I've connected a start button. Then I come back again and say I have a stop button as well. Stop. And then I connected it on percentage I O dot 1.1. Then I come back again and say I have a E stop. I've connected it on I 0.1.2. Then I come back again and say I have overload. I've connected it on percentage I O dot 1 dot 3. And if I go to this module, you see I have a start button, stop button, stop, and overload. On the DDO, let's click on the DDO is nothing connected because I haven't declared anything. I come back here and declare, and I say I have a motor coil. It's a motor C. Click enter, and then declare it. When you declare an output, you're gonna say percentage Q 0 dot, what slot is the this one? This is on slot number 2, and then let's say I've connected it on digital output 0. Then that's it. That's how you declare your variables. And if you go back to that DDO module now, you can see this motor C there on digital output 0. All declared. And then now we have to create the logic. For us to create the logic, we're going to come here and go under programs. And then under must, we're going to collapse the must. And then we right click on the logic, new section. And then we're going to just say, okay, this is pump 1, for instance. Just give it whatever name you would have in your mind. And then as you can see, we're going to select which language we want to use. In our case, we said we're doing ladder diagram. And we're going to click on LD and then OK. And then this programming section will pop up. Then as you can see on top there, we have contacts that we need. And then we're going to click and the normally open there. Then we're going to add the normally open here again for the latch. We need the normally close for the overload, for the stop, for the e-stop. And then we need a coil for the motor. And then link that. Then we're gonna double click to give them the variables that you've declared. Double click and then select there, and then we say this is a start. Okay, that's a start. And then double click here and then say this is an e-stop. Okay, double click there and say this is a stop. Okay, double click there and say this is an overload. Okay, then double click there and say this is our motor coil. And then okay, it's normally open for latching. And then we double click and then we click on the motor C as well. And then that's it. And then if you can see, if we're still together, the project says it's not built. And then we're gonna come back here and say, can you please analyze the project if everything is fine? If everything is okay, you'll have 0 errors and 0 warnings. And then we are on simulation mode. And then the project says I'm analyzed. And then let's just build the project. Rebuild the project. The project is built, it's green. And then we're gonna come back here and try to connect the PLC. We're gonna say PLC set address. If you are in real life trying to connect your PLC, you would have to say I have a PLC. I'm trying to connect via USB. If you're connecting via USB, you'll leave everything as is. If you're connecting using TCP/IP, which is your Modbus, your Ethernet, you're gonna come here and say TCP/IP and declare the address of the PLC. If you are using Modbus, you're gonna come here and say Modbus, depending on whatever that you're trying to communicate by. If everything in terms of a communication is correct, you're gonna come and say test connection. You'll get this kind of a pop-up. If your connection is not correct, for instance, because now we're communicating with the simulator, let me just put the wrong address. As you can see, the address there is 1270.0.1. Put it as a 0 there. Test connection. If you are not communicating with a PLC, you'll get a prompt like this. It will be like that. That means your connection is not successful. Then let me put back the correct address there. and then that will be 1, and then here's the connection. You can see the connection is built, and then okay, go back to PLC and then connect. Now we are connected. But now what it says different. That means what is inside the PLC and what is in the project layout, they are not the same. For me to make them the same, I'm gonna transfer the project to the PLC. Transfer the project to the PLC, okay. Then the transfer will happen. Then the transfer is done, and then we confirm that we want to be on a running mode. Now we are on a running mode. In green, it means power is there. It reaches here. This side in red, that means there's no power. Now you come, you press your start button, set value to modify the value of the start button, and then we set it to high. And then it's on. Now it becomes green. The coil is energized. We are latching. The start button is out. You come here, and then you when you come to your stop button, and then you set it to high. You're stopping. That means you press your e-stop, and then you coil to get de-energized, and then you reset the e-stop. You come, you press the start button. You can start. The start button is released, and then that's how we do our ladder logic or ladder diagram. And then I hope the practical was successful and delivered the message or the lesson that needs to be learned. Till we meet again, that is all for today. I thank you, and please subscribe to our YouTube channel. Thank you very much. More practicals to come. We're gonna do the same ladder logic with IPS soft, which is the Delta version of the PLC. I thank you. But before we deal with the Delta one, I wish we can continue with the Schneider one, doing the function block and the other programming languages. I thank you very much for choosing KA Academy. Goodbye.